So good morning, everybody, and welcome to another exciting broadcast with us here at Exploring by the Seat of Your Pants. We did 32 programs together in September alone. It was a wild and crazy month, and we are diving headlong into our thrilling space-themed October extravaganza. We just wrapped up this morning with Nicole Stott, astronaut and artist. You can check out her program on our YouTube channel. One of bevy to come with amazing NASA personnel, more astronauts, and more. It's a really exciting chance to learn about the majesty of the cosmos, get involved and excited. Now, today I'm really excited for a number of reasons. First and foremost, we're going to have a Kahoot again. So if you're joining us live on YouTube, if you're joining us live in the classroom, if you want to type in this game pin into one of your separate tabs, in about 20-25 minutes, we'll have the chance to play along with a little 4-question quiz, test your understanding, have a little bit of fun, keep it extra interactive. I'm also excited because we are announcing today, officially for the first time, our return of our epic art contest. So last year we did this amazing opportunity for kids to draw what they wanted the James Webb Space Telescope to look for. We had 660 submissions from, I think, 7 countries or something like that. It was crazy. Make sure you check this out below. I'll make sure that link goes to all our registered classes as well. But a very exciting kickoff to the art contest again for this October. But most of all, I am thrilled as we are welcoming back possibly my very favorite educator in the world. Now, don't tell the others. They're not here, so they're unlikely to watch this broadcast because they don't want to get too jealous. But Nathalie Ouellette is just an incredible public educator. I don't think there's anyone in Canada who's done more to get people excited about space than she has. She's everywhere. I can't go 10 feet without running into something that Nathalie has done. So you guys are in for such a treat today as she talks about the amazing James Webb Space Telescope. She's the lead outreach scientist for all of Canada on the JWST. She's done a bevy of broadcasts in the past, and I'm so excited for over 550 of you today to hear from her about the amazing telescope and all her work. So without further ado, Nathalie, welcome back to Exploring by the Seat of Your Pants. And unmute with us and take us away.
All right, you can hear me now?
I can hear you now. You're golden.
Perfect. So I'm super thrilled. I think it's been like over a year since I was talking to you all through Exploring by the Seat of Your Pants. And so it's always a great pleasure to be with all of you, talk about space, get you all excited. And you might think, oh no, she's talking about the James Webb Space Telescope again. Trust me, there has been a lot of action in the last year. It's been so busy. There's been so much science, lots of incredible discoveries. And so we'll be going through some of those. It's just really the tip of the iceberg, though. And I'll give you a link at the end if you want to try and stay up to date on all the cool stuff that's going on with the telescope. So I am an astronomer or an astrophysicist, and astronomers use telescopes to study the universe. And for the longest time, astronomers have been using telescopes to look at one particular kind of light called visible light or optical light. And that's the same kind of light that we can see with our naked eye, the human eye. But we now know that there's all different kinds of light out there in what we call the electromagnetic spectrum. So you might have heard of some of these kinds of light, like X-rays, gamma rays, infrared light, ultraviolet light, even radio waves, which we tend to associate with sound, is a kind of light. Now, they're invisible to our eyes, but that doesn't mean that the universe isn't chattering away in these kinds of light. So in order to really understand everything that's going on out there, we need special tools to look at these kinds of light because our eyes can't do the job. So we build such tools, and one such tool is the James Webb Space Telescope. Now, it's looking at an invisible kind of light called infrared light. And infrared light basically gives you magical powers, and I'll explain some of those magical powers, but you're able to see not only things that are invisible to the human eye, but also you can see through other materials, almost like an X-ray. So the James Webb Space Telescope, or Webb Telescope, or JWST, is an international collaboration. These big missions usually are, and it's led by NASA. NASA is the American Space Agency. It's the biggest space agency in the world. They've been doing lots of really great work. They're leading us going back to the moon with the Artemis mission, but Canada's part of that too. There's also the European Space Agency, which is lots of different countries working together in Europe. And they together built one of the most important space telescopes before Webb, which was the Hubble Space Telescope. But for the JWST, very exciting for us here in Canada, the Canadian Space Agency is a partner. And so that means that we were involved in building parts of the telescope. We're involved in doing lots of the science with data and images from the telescope now. So we're going to continue to be involved. It's really, really exciting. And that means that everyone in Canada should feel like they're a part of this mission. This telescope partially belongs to us. So as Jesse mentioned, I'm the outreach scientist for the Webb telescope in Canada. I'm an astronomer, so I study galaxies, how they form, how they evolve, and I got my PhD in astrophysics now 7 years ago, a little while ago. So I'm part of the science team, but my role is to sort of act like a bridge between the science team and the rest of the world, the general public. So we want to make sure that everyone gets to enjoy the wonderful discoveries that are coming from this telescope. And so we want to put the images publicly online. We want to do media interviews so that they go on TV. We want to do social media content and presentations like today so that you know what's going on with the telescope. So this is a picture of me visiting the telescope before it was launched into space. And you can't really see it because of the perspective, but this is a really, really big telescope. Its golden mirror is about 6.5 meters wide. That's really a lot taller than a person. And the big silver piece that you can see on the bottom is actually its sun shield. So I mentioned that this telescope looks at infrared light. Now, infrared light is very sensitive to heat. So that means if this telescope gets heated up by, say, sunlight, it will start shining in infrared light itself. Humans, for example, shine in the infrared light. So the telescope would actually see you and me very, very well. But if it was shining itself in infrared light, it would basically be causing its own sort of light pollution, and it would stop it from being able to see lots of cool stuff in space. So that big sun shield protects the telescope from the sun, and it's about the size of a tennis court. So the whole thing is about 2 stories high, about the size of a small house, and it's out there floating in space right now, 1.5 million kilometers away. Now, obviously, this was taken before it was launched into space, so I got to visit it while it was being tested in a lab in 2019. So I really like this picture. It brings back good memories for me. But one picture that I like to show that shows my commitment to the mission is this one. This is my Halloween costume from October 2021, just a few months before the telescope was launched into space. And what I love about my job is I have the freedom to sort of talk about the telescope in lots of personal, creative, funny ways to try to sort of inject my personality in what I do. And so I built a scale model of the telescope and I gave out candy to trick-or-treaters at Halloween. And it gave me an opportunity to talk about the telescope while kids were coming to my house to get candy. So I want to show people that science is fun, space is exciting, and all kinds of different people can be scientists. It's not just like the image that you might have of what a scientist or an astrophysicist looks like in your mind. So I mentioned Canada is a part of this mission. And so in 2012, we delivered one of the 4 instruments that are on the telescope. So on a telescope, you can have the big mirror, of course, that collects all the light, but you often have a bunch of little instruments that takes that light and make science out of it. So they can be cameras, they can be special tools that break down that light called spectrograph. And so this is the Canadian instrument, and it's actually a double instrument. It's a 2-for-1 deal. So it's that golden part in the middle of the image. And on top, you have what we call the fine guidance sensor. It's a guiding camera that we nicknamed FGS. And it's basically the eye of the telescope. So the telescope is moving around in space and it's trying to take a good, clear picture of something very, very far away. But imagine you're taking a picture with your phone or a camera and you're sort of shaking the camera around. You're not going to take a very nice picture that way. It's going to be a blurry picture. So what you need to do is you need to have an eye that can compensate for that movement to make the image nice and clear. And that is what the FGS does. And it does it with a huge amount of precision. It could basically be able to see someone in Toronto wink at you if you were in Montreal, about 500 kilometers away. It has a very, very precise eye. On the underside, you have the near infrared imager and slitless spectrograph, and that's a fancy way to say that it's both a camera and a spectrograph, that tool that breaks down light and gets even more information. And it looks at a kind of light called the near infrared. So the whole thing is about the size of a dishwasher, and it's at the center of all the instruments at the back of the mirror of the telescope. So hundreds of people have been working on the Canadian contribution for years and years. The Canadian Space Agency, where I work at the University of Montreal, we were the lead academic partner, but there's also the National Research Council in Victoria and industrial partners like Honeywell Canada as well. Now, what is Webb observing? That's what we really want to know. Now we are actually in space. We can take data, we can do science. And one thing that I love about this telescope is that it's not just a one-trick pony. It can do all kinds of different things, different kinds of objects. So we can sort of break it down into 4 main categories. So alien worlds, that's a very, very popular one. It can be worlds that are inside of our solar system. So anything that's not Earth, essentially. It can look at Jupiter, Saturn, comets, asteroids, Pluto, but it can't look towards the sun. So there are certain things that it can't look at, otherwise it would fry its instruments. So it can't look at the sun, Mercury, Venus, the Earth, so it can't look back at us and say hi, and the moon. But everything else in the solar system, it can look at. But there are also worlds that are outside of our solar system. You might have heard about them. They're called exoplanets. And so there are other planets that orbit stars other than our own sun. So there are other stars out there, and now we know that there are planets orbiting those stars. We also want to understand those stars themselves. And so stars are born, they live out their lives, and they eventually die. And depending on how big they are, they have different deaths. But you'll see in a few minutes, many moments in a star's life is very, very dusty. There's lots of dust and gas all around. And we've been experiencing a lot of forest fires in Canada this year, right? When there's dust and gas in the air, can you see very well? No, everything's kind of hazy around you, and the light is being blocked out. Well, one of the magical powers of infrared light is that it allows you to see through that gas and dust. And I'll show you some images that explain that. We also want to understand galaxies. So that's what I study. And one thing that I love about galaxies, I sort of think of them as sort of animals. They are born and they evolve over time, over billions of years, but they are usually born inside of groups, sometimes groups of 2 or 3 or 4, sometimes these huge groups we call clusters, where thousands of galaxies live together. So you can sort of imagine like a herd of elephants, and they're all interacting with each other. Sometimes they fight, sometimes they merge together and make bigger galaxies. And so we want to understand how galaxies evolve through the entire history of the universe. And that brings me to my last point, and this is one of the reasons why we even imagine building the Webb telescope. We want to look back as far as possible in the early universe, farther than any telescope ever before. And how do we do this? We can look far in distance, but how can we look far in time? Well, one thing you might know or not is that telescopes can actually act as time machines. Because the things we're looking at are so far away, it takes a long time for their light to get to us. Even though light is the fastest thing in the universe, it takes some time to traverse or go through the large distances in space. So if I say, for example, a galaxy is 10 billion light years away, that means it took 10 billion years for its light to reach us. That means that the light that I'm seeing, or that my telescope is seeing, is 10 billion years old. So I'm not actually looking at that galaxy as it is right now. I'm looking at it as it was 10 billion years ago. So with the telescope, with Webb, we can actually look back almost to the Big Bang, which is like really fantastic. And we've been discovering a lot of weird stuff close to the Big Bang that we weren't expecting. So now I'm going to go through some of my favorite discoveries and images taken by the telescope in the last 14 months since it started its scientific mission. So I mentioned it can look at things in our solar system. And so Neptune and Uranus are two what we call ice giants. They're smaller than Jupiter and Saturn, and they're colder as well. So they're these beautiful blue colors. They both have rings. Not only Saturn has rings. You can see here on the left, this is Neptune, and you can see 7 of the 14 moons of Neptune. So you have 6 that are around here, and Triton, which looks very bright. It's the largest moon of Neptune. Here, you can see Uranus. It has moons, but you can't see them in the picture. And you'll notice its rings are going in the other direction that we're used to. And that is not because we flip the image. The rings are actually like that. It's because eventually, in some point in Uranus's life, it was knocked over on its belly by, we think, a big asteroid. And now it's sort of like rotating on itself on its belly instead of turning around like this, like all the other planets. And its rings are on the other side as well. So this is a really, really cool thing with Webb. We've never sent dedicated probe missions to these planets. And so these are the best images we've had of these planets in over 30 years. We haven't had something pass by them since the Voyager probes in the 1980s. And we've discovered lots of things have changed in the last 30 years on these planets. This is the largest planet in our solar system, Jupiter. You might notice it's big, what we usually call a red spot, but here it looks white. It looks white in this image. You can see all the clouds that are going along its surface here, and they're actually northern and southern lights on all of the planets, most of the planets, but including on Jupiter. You can see them right here in the north and here in the south. It also has rings. You can see it there. It's a beautiful image, but I don't want to actually emphasize the image itself, but rather who took this image, who created this image. So the data was, of course, taken by the Webb telescope, and we have lots of great people taking that raw data, which is really just a bunch of numbers, and making beautiful images. But most of this data becomes available almost immediately to everyone online, to the public. So even you could learn how to make an image like that from the data from the Webb telescope. And so this is what this student, this woman, Judy Schmidt, she's a student not in astronomy. She lives in California. She's just a big space lover. And for the last 10 years, she's taught herself how to take data from a telescope. She learned how to do it with Hubble Space Telescope data and how to make images herself. And so she made this image without the help of anyone from NASA or any other space agency. And everybody loved it so much, it's been integrated sort of in the official images. So if you really love space and you want to learn to do this yourself, there are resources online. And so don't think that you have to wait to be an adult and 30 years old before you can start doing cool projects. There's so many resources online, you can start doing it yourself. So I mentioned there are alien worlds in our solar system, but also outside of our solar system. And this is what we call an exoplanet. Now, unfortunately, these worlds are very, very far away. So we're talking, it would take like tens or hundreds or even thousands of years to get from them to here. And so we can't take nice pictures of these worlds like we can for our own solar system planets. So we sometimes imagine what they might look like in illustrations like this. So you might think, okay, we can't see them. How do we know they're there? So we use what we call indirect methods. And one of the best ways to do that is through what we call the transit method. So this happens when a planet passes in front of its star and blocks out part of that star's light. And depending on how big the planet is, the dip in the brightness of the star can be bigger or smaller. Now, we don't actually see that black dot go over the star, but what we do see is we measure the brightness of the star go down. Now, this is a good indication that something passed in front of it and blocked the light. And that little dip in the brightness can tell us really cool information, like how far that planet is from its star, how big the planet is as well. And there are other methods that allow you to measure things like the mass of the planet too. Now, another thing that we can do when that planet passes in front of the star is we can see how the atmosphere around that planet affects the starlight, because the starlight will pass through a part of the atmosphere of that planet. And then we can take that light, break it down using some of the instruments I mentioned, like a spectrograph, and we can actually measure what's inside the atmosphere of that planet. So people using the Webb telescope did that for this planet here called WASP 39b. It's a really, really big planet, so we call it a Jupiter, but it's very close to its star. It only takes about 4 days to go around its star, and it's 900 degrees Celsius on this planet. So I wouldn't want to live there. But because it is so hot and so big, we call it a hot Jupiter. And it has a puffy atmosphere that makes it very easy for us to study. So hundreds of people around the world studied this planet last year, including many of my colleagues at the University of Montreal. And they were able to determine all kinds of cool stuff in the atmosphere of that planet. So this is what those spectrograph instruments give us. These are called spectra. And all of the bumps and wiggles, you can imagine them sort of like a fingerprint. So one of the instruments used was the Canadian one that you can see in yellow. And all of those bumps and wiggles tell us specific molecules that are in the atmosphere of this planet. So things like carbon dioxide, what we exhale, is in this planet's atmosphere. Potassium, the same potassium you have in your bananas, in this planet's atmosphere. Carbon monoxide, even water vapor. And we were able to do this for a planet 700 light years away. But of course, this is not really a good planet to search for alien life. So we've been able to do this kind of study for all kinds of different planets, including some that are smaller and maybe more Earth-like. And just a few weeks ago, this is like a brand new result. We published this result of this planet called K2-18b, and it's what we think is an ocean world. That means that on the surface of the planet, there might be just a big, thick layer of liquid water all around it. And so we did the same kind of study. We took the light, we broke it down with the spectrograph instrument, and we made another sort of fingerprint for the atmosphere. And so we found lots of cool stuff again using partially the Canadian instrument. We found methane, so the same thing that comes out of cows, we found in here, carbon dioxide. But one thing that is really, really cool and exciting and promising is we detected a molecule called dimethyl sulfide, or DMS. And on Earth, the only thing that can create DMS is life, biological, organic life. Now, does that mean that it can be created another way elsewhere in the universe? No, of course. Maybe there's other weird stuff going on this planet. But potentially, this could be the very first detected sign of biological or alien life by the Webb telescope, or even by any telescope. So we still need to do more studies to see if this is a real signal and if this is really created by life. But this is basically a new chapter in the search for alien life. We are maybe seeing the first signs of alien life using the Webb telescope. Now, going to stars instead, I mentioned that stars are born, they live a certain amount of time, and they eventually die. So where are stars born? They're born in these big regions called nebulae or nebulas, where there's lots of gas and dust. And all throughout that gas and dust, things are collapsing and forming into stars. So this is my favorite picture taken by the Webb telescope up until now. It's called the Pillars of Creation. And hundreds of stars are being born all throughout these sort of pillars of gas and dust. Now, this is what it looks like using the magic of infrared light. But we studied this region before using the Hubble Space Telescope, which can look in visible light, just like the human eye. And you can see the big difference in these two images. Here, you see a lot fewer background stars. That's because all that gas and dust are blocking out that light. But with infrared light, like I said, it's sort of like having X-ray vision. You can see through that gas and dust, and you can see the stars being born in the first few million years of their lifetime, which we've never been able to do before. Now we can have an even closer look at some of these stars that are being born and look at sort of individual solar systems being born. So both of these are solar systems, stars that are being born, and the birth of a star is not a quiet thing. And the birth of a human is usually not a quiet thing either. So yes, the star is gaining more material and it's building itself up, but there's lots of material that's being blown out as well. So this is why you have this sort of hourglass shape. At the very center, you might see a little black line. That's the size of the solar system. This is the solar system being born. But you have all this gas and dust and energy being blown out from the sides there. And the same thing happening here. This is about the size of the solar system right here, and you have all this energy being blown out. But eventually, things will calm down, and then potentially planets will form and maybe even alien life. And then the star will continue its evolution, and eventually it'll die. So, depending on how big it is, it might have a sort of standard death, like our sun will have, where it will blow out its outer envelope of gas and dust into sort of a circular shape, like these ring nebula. And eventually, all you'll have left at the center is basically a zombie star called a white dwarf. It's very hot at the start, but it can't produce any more energy or heat, so it just keeps cooling down forever. But if you have a star that's even bigger than our sun, it can blow up in something much more explosive called a supernova explosion. And at the end of that, you have what we call a stellar remnant nebula. So here, all you see in the colors are sort of like the guts of the stars that have been blown out all over the place. But don't worry, all that material will eventually be recycled and turned into new stars. Now, you can also study galaxies. So I mentioned galaxies are often in groups and they're interacting together. So this is the cartwheel galaxy. You can see why it's called the cartwheel. There's the circle around here and in the inside with all the spokes of the wheel around it. And this is a very rare kind of galaxy called a ring galaxy. And the reason why it has this big ring is this little guy passed inside of the big one and caused a big burst of fireworks of new stars being formed on the outside. So you can study how these galaxies are interacting together. And these two here are actually merging together. So they're two big galaxies that will turn into one even larger galaxy eventually. So we can see how galaxies evolve over time as they interact with each other. Or you can study lots and lots of galaxies at the same time. And this image is called the Webb Deep Field of Galaxies. And there's, sorry, oh, it's the best
I was
image.
just going to say it's the best
muted.
image ever, Natalie. Sorry, I just want it's my favorite thing in all of science, and I'll.
Yeah, it's a really fantastic image, the Webb Deep Field of Galaxies. And in this image alone, there's 7,000 galaxies. Now you might think, okay, it's a big part of the sky. It's not that impressive. No, no, no. This is the equivalent of taking one grain of sand on the tip of your finger, you hold it at arm's length, and that part of the sky you're covering with a grain of sand is that image. 7,000 galaxies here, and so many galaxies with so many different colors. Some are closer, some are farther away. And so just come back here. Some are closer, some are farther away. And so you'll see some of them have sort of like these weird shapes. And that's because all the galaxies that are closer to us are bending the light of the galaxies farther away. So lots of different things that you can study in here. So as I mentioned, this is just the tip of the iceberg. There's lots more to discover. So you can follow all their latest results at this website, www.webbtelescope.org. Now you'll remember, this telescope can see lots of different things, very, very cool. But now we want you to decide what the Webb telescope should be looking at. So Jesse will talk a little bit about it more, but I wanted to personally invite you to participate in this really cool contest where you can print out this paper, and then you get to draw inside one of the mirror pieces of the telescope what you want the telescope to look at. So you can submit your drawings by October 30th, and there's lots of awesome space prizes to be won. I can't wait to see your pictures.
Me either. Natalie, that was so much fun as always. What an incredible tour. Sorry to pop in there. The deep field is the coolest thing in all of science. I think if you really understand the deep field, it is like the greatest single picture we've ever taken in history. Also, how many Jurassic Park things do you have? The poster, the mug. It's very exciting.
I have a lot. I haven't found a place to put him yet, but I also have this really cool medieval dragon that I'm trying to incorporate into my background.
Incredible. It's a gift to the world. Thank you so much for all this. As we said at the top, so much to do. We're going to do a little Kahoot together, test your understanding, have a little bit of fun, 4 quick questions, and then we are going to go live to our classes, to our YouTube classes, Miss Wells' class on YouTube. We've got Miss Malco's class in Wisconsin joining us today, Mr. M, our Merida, Mexico class. I'm so excited to take questions from you all. Nathalie, if you want to exit screen share and have a bit of it, like if you can see us again, great. But this is fantastic. We are going to dive in. For those who are new to Kahoot, the faster you answer, the more points you get. And what you win is Nathalie and I's everlasting respect. So that's worth a lot. It's pretty fun. I'm pretty sure all of these were directly in your thing. I made this up before we had a chance to go through the presentation today, but I think we're pretty good. If you're on YouTube especially, be quick with these. What kind of light does the James Webb Space Telescope look for? Radio waves, visible light, ultraviolet, or infrared? I will note too, for Kahoot fans, we've got a permanent Kahoot with Nathalie that is on our permanent Kahoot page that has like thousands and thousands of plays, which is awesome. So if you want to check that out, I'll make sure all our classes have that too. All right. The answer is infrared. Oh, we spoke to a few people with this one. Ultraviolet was the least. Infrared is correct. The one that we emanate. We glow. Infrared. It's beautiful.
Yeah, we glow in it. The Earth glows in it.
It's so freaky. It's weird to think about it that way. That took me a long time, actually. That was like a cognitive dissonance thing. I couldn't understand it. So I'm glad we cleared that up for our kids really early on. Telescopes can look back in time. True or false? Easy. 27 answers, 30 answers now. Oh, so many of you. 6 more seconds. I mean, would we throw it in there if it wasn't totally true, Nathalie? I don't think so.
Probably not.
Pretty weird out of context. Most of you got this. So yes, we look back at things that are so far away that the light takes that far to get at us that we're not looking at them as they are now. We're looking at them as they were in the past, which is really counterintuitive and freaky. One of the magic things about space exploration and understanding. But way to go to all of you who got it. The universe is how old? How with this? Jeez.
I don't think I mentioned this. We're exactly.
New ones. 1.7 million, 13.8 billion, infinite and ageless, or 560 million. I decided to throw some like more nuanced ones in here. Ooh, we tripped a lot of people up. I like infinite and ageless. A lot of people got this right. Nathalie, actually, I want you to clear something up for me because when you look this up, it was 13.7. Now a lot of groups are like 13.8. So is it like 13.75? Do we have a thing on this or not?
I think it's like 13.78 or something like that. And like it used to be like, oh, it's about 12, it's about 14. We're like trying to narrow into like a more specific answer.
Okay, but way to go to most of our folks that got this. Going to our final question, and then we're going to Mr. M's class first. That threw up our leaderboard entirely. Oh, Power Bobcat takes a lead. Spoiler, playing spoiler. Final question. How long would it take the fastest spaceship we've ever made to reach our nearest star? So we're looking at these things because we can see things at the speed of light, and that's great. If we took the fastest spacecraft we've ever made, is it 4 months, 11 years, 350 years, or over 70,000 years? Surely can't be that long, can it, Nathalie? No.
I can mention that the nearest star is about 4 light years away.
Which, ooh, nice even thing. Like Voyager, so New Horizons is faster than Voyager now, I think. It's like the Pluto one was like the fastest. But in any case, it's
the Parker Solar Probe is the fastest one now.
Ooh, we just keep making faster stuff. We're good at that.
Yeah.
That's our trick. But it's thousands and thousands of years, which is why we need these tools to see them, because you can't just hop in a bus and go. It's very tricky to get there.
Yeah. And it's also why we cannot plan on moving all of humanity to these planets after we ruin the Earth. We cannot, so let's take care of the Earth, please.
Take care of the Earth. It's very important. You're not even going to Mars to move all the people. Like, Earth's the important one. Great job to any of those 3 who might have won. Let us know who you are in the chat. We're going to go to Mr. M's class, and then we're heading to Mr. Nunez's class right after that. Come on in, guys, and take us away, Amazing Force. Hi.
Hi.
Hi, my name is Arohi. How does the telescope fly?
Ooh.
So that's a great question. So in space, it's kind of nice. You don't need to constantly be using fuel to stay afloat because there you can just float around in space. There's no gravity as long as you're not close to a planet or a moon or anything like that. So the real challenge was to put it in space to start off with. So what we needed to do is we needed to take the telescope, put it on a rocket, and then send it out into space. And once it's in space, it only needs a little bit of fuel to sort of redirect where it's pointing, but it's actually not too bad. But really, it was the rocket launch that used up a lot of fuel. And one cool fact is the telescope is so big, it actually couldn't fit inside the rocket. So we needed to fold it up on itself to put it inside the rocket. And once it was launched, then we needed to unfold it, which was super complicated, but it all worked well.
That was the most nerve-wracking part for me, is like the origami section of the whole thing. It's like, we've done rocket launches
Yeah.
before. We've never done anything like that, have we? Like, there's nothing.
Not to that degree of complexity. It's like it was 300 different doodads that needed to deploy.
I'm nervous just thinking about it in retrospect, which is a good problem to have. Let's head to Mr. Nunez's class. Welcome in, guys. Unmute your mic. And so nice to have you joining us in Mexico today.
How the universe
Hola.
can explore.
Oh, unmute again. We missed it.
How the universe can still expand and be infinite at the same time.
Ooh.
So we're not actually sure if the universe is infinite. So it's sort of like us trying to see what the shape of the universe could be, but because there's a limit as to how far our tools like telescopes can look, we sort of hit a wall. But we know the universe is actually bigger than what we can see. There's what we call the observable universe, which is about 96 billion light years across. And we think that there's a universe beyond that. But because we can't see it, we can't make any measurements, and we don't know how big it is. But we do think there's maybe a certain size that it has. It's not necessarily infinite, and that size keeps getting bigger and bigger and bigger. But it's sort of just guesses at this point because we can't see it, unfortunately.
I love when we have questions like this that are really, really in depth. And it's hard to answer this in 1 minute. You did a fantastic job with that. But good question, guys. And again, there's tons and tons of books, online resources. NASA does an amazing job. They got some of the best outreach resources in the world to check things like this out. So if you want to follow up with that, please do. And I can recommend some books. Have your teacher email us and we'll get you some info on that. We want to head to Van Buren Elementary in Wisconsin. Ms. Malco's class wants to know, how long is the telescope expected to function, and could it be fixed if something hit it?
So also a great question, because this telescope is so far away from us that if something goes horribly wrong, we can't actually fix it. We were able to fix the Hubble Space Telescope when it needed it because it was just only about 520 kilometers above the Earth, only, which is, it's not too bad. It's like a distance between two major cities in Canada. So this telescope, the limiting factor for this lifetime mission, the length of its mission is how much fuel it has, because it does need a little bit of fuel to adjust its trajectory. So when we first launched it, we were thinking, okay, we're hoping for like something like 10 years, but the launch actually went so well. We saved on a bunch of fuel, and now it has enough fuel to last something like 25 years. We don't know if the instruments will last that long, but that's really exciting. Like, we think it'll last longer than we originally expected. Now, in terms of things hitting it, we knew that there were going to be very small asteroids called micrometeoroids in space. And so we tested all of the parts of the telescope very, very thoroughly in a lab so that they could be resistant and durable if they got hit. Because we knew that it was actually going to get hit on average like once a month. And we have been seeing that. It has actually been hit quite a few times since we launched it. But because we tested it and chose materials that would be resistant to it, it's doing a great job and it's not really affected its operations.
Very, very cool. And it's amazing that you can know that we have knowledge of the universe enough to be like, this is how much we expected to get hit. And then you can verify that with like the actual instrument out in space. That's very cool in and of itself. Like, whole different talk on that.
Yeah, but it's not a complete part of our knowledge. And so on top of all the cool astronomy that the telescope is doing, it's becoming a micrometeoroid sensor or detector to inform future missions on how many little space rocks there actually are out there.
Fantastic. I love it. Mr. M's class, we're heading back to you. We're going to go to Mr. Nunez again right after that. Come on in, guys. Hey.
Hi,
Hi.
my name is Het. How much time do you take to make the telescope?
Ooh.
So these missions take a long, long time. So the Hubble Space Telescope was launched in 1990, so 33 and a half years ago. And as soon as the mid-1990s, like 1995, 1996, people were thinking about what would replace or be the next big telescope after Hubble. And that's when we started thinking about the Webb telescope. And then people started really building things in the early 2000s. So between the idea of the telescope and when it was launched in 2021, we're talking like 25 years. So it takes a long time, but then it works for hopefully 25 years, and like a new generation of astronomers can use it.
I don't know what prompted it, but I saw like the original pitch meeting for the James Webb Space Telescope, and it was like the next gen telescope the other day, and the outfits people are wearing in the mid-90s, and like thinking about the high-tech telescope that's out there now, and like this peak 90s Friends era time is just amazing. So I'm really glad we
people will look back at what we wear now and make fun of us too.
Absolutely. Mr. Nunez's class, come on back in and take us away. Hey. Yeah, come on mute.
Hello.
Hi.
What happens when a star dies naturally?
Ooh.
So I like that you specify naturally. Maybe you're thinking of like star destroyers in Star Wars. As far as we know, stars can only die naturally. And so it depends on how big the star is. But near the end of the life of a star, basically it starts running out of fuel. It can't really produce a lot of energy and heat anymore. And so at that point, there's nothing sort of pushing out on its boundaries. And it just sort of wants to like collapse in on itself and sort of like give up essentially. But if it is sort of a medium-sized star like the sun, what it'll do is the outer part of the star will sort of blow off. And that is what creates that sort of like round nebula or that ring nebula. We call it a planetary nebula. And so at the end, all you have is that zombie star, like a white dwarf that's left over that just keeps getting colder and colder and colder. But a bigger star than the sun will blow up and just spread all of its guts all around. And that's going to eventually be recycled into new stars. But you can also be left with a zombie star at the center. It can either be what we call a neutron star, which is a very, very dense star, or it can even create a black hole. So that's how we create black holes. They're the leftover zombies after the death of a really, really massive star.
Cool. If our kids want any more information on this too, we actually on our YouTube channel, we just did a program with an astrophysicist at Caltech, Mike Grudich, the other day. It was amazing. Talked all about star formation and more. And Nathalie, in your talk, I'd actually never heard someone describe that gorgeous nebula as like what will happen to the sun, what it'll look like. That's so cool. I've never seen that linked together. That's beautiful.
Yeah, we better hope that humans aren't around to see it too close up though, because it wouldn't be good for us.
No. I wish we could take questions all day long. Time flies and you're having fun, and so I will wrap up there. But I did want to note, if you guys want to check out this program later, it will be on our YouTube channel. You can share it with your friends and family. If you've got French colleagues, we're doing a program with Nathalie tomorrow in French, same topic, so please do come tune in for that. And as Nathalie was kind enough to mention, we've got this amazing art contest. If you want to sign in, share your drawings over the next few weeks, we'd love to have you in the month of October. A partnership between us, the Institute for Research on Exoplanets, Nathalie's group, and Discover the Universe. So a big thank you to them for joining us yet again. A really cool opportunity to learn more. Webtelescope.org, all the cool James Webb Space Telescope. And Nathalie, as we do to wrap up every podcast, I'm going to bring in our classes to say a big thank you and farewell. Mr. M's group, Mr. Newton, groups, thank you so much, everybody. Have a wonderful day.